Linear and angular speed. In this lesson, you will learn how to use radians to find the linear speed of a point on a circle, and how to use radians to find the angular speed of a ray rotating around the center of a circle. Remember that speed equals distance over time. So here we have a point being rotated around the circle, and that creates this arc length, and the circle has radius r. So our point is moving along the outside of the circle, the edge of the circle, and so our linear speed is how quickly it's moving along that circle. So we take the arc length over how long it took to create that arc length. So our linear speed is arc length over time. We use the variable v for velocity to represent linear speed. So v equals s, which we know from previous lessons, represents arc length over t time. Then we have angular speed. Angular speed is how quickly this ray is rotating around the circle. So our angular speed is the amount of rotation, this angle measure, over time. How quickly does the angle become this angle measure? How much time does it take for it to become that big? So angular speed equals the amount of rotation over time. And we represent that with omega. That's this little guy here. It's a Greek letter called omega, and that equals theta, which was your amount of rotation, your angle measure in radians, over t, which was your time. So angular speed is omega equals theta over t. All right, suppose the point P is on a circle with radius 7 inches, and ray OP is rotating with angular speed pi over 12 radians per second. Find the angle generated by P in 8 seconds. Well, first we know that omega is pi over 12 because they told us the angular speed was pi over 12. And feel free to draw a picture if that helps. Remember that omega equals theta over t, and we're trying to solve for theta. We know what t is, so we can say omega was pi over 12, and that has to equal theta over 8. Remember your transitive property. If omega equals pi over 12 and omega equals theta over t, then pi over 12 equals theta over t, which we can plug in the 8 for the t. So when we multiply, we get theta equals 8 pi over 12, which equals 2 pi over 3 radians. Next we're going to find the distance traveled by P along the circle in 8 seconds. Remember that our arc length is radius times theta, which is the angle measure. So we know that our radius is 7. The original problem told us that. We know that theta equals 2 pi over 3. We just found that. So that equals 14 pi over 3 inches. So that's the distance traveled by P along the circle in 8 seconds. Now we want to find the linear speed. So we have velocity equals the arc length over time, and we know that our arc length was 14 pi over 3, and our time was 8, and that was in seconds. So we can rewrite that as 14 pi over 3 divided by 8, which is the same thing as 14 pi over 3 times 1/8, and then we can simplify that, and we get 7 pi over 6 inches per second. A belt runs a pulley of radius 9 centimeters at 112 revolutions per minute. Find the angular speed of the pulley in radians per second. So, well, we know that our pulley is rotating 224 pi radians per minute because it's making 112 revolutions, and there are 2 pi radians in 1 revolution. So then we can take that and put it into our angular speed formula, where we have omega equals, and then we put our arc length, which is 224 pi, over our time, which is 60 seconds, because we knew that it was rotating 112 revolutions per minute, but we want our answer in seconds, so we just multiply that minute by 60 to get 60 seconds, and then we just simplify the fraction. And we get 56 pi over 15 radians per second. That is how quickly the angle is moving. Then we're going to find the linear speed of the belt in centimeters per second. So we just found the angular speed of the pulley. Now we're looking at the linear speed of the belt. How quickly is the belt moving? So we take our formula, velocity equals arc length over time. We know arc length is r theta, and we know that we can use our properties and say that r is multiplied by theta over t, because we just found theta over t, because that is omega. So we can just plug in our 9, our radius of 9, and then our omega, which was 56 pi over 15, and that gives us 168 pi over 5 centimeters per second. So this is just another way of using algebra to manipulate the equation. We knew that v equals s over t, and then we can change s into r theta, and then we know that we can multiply the r by theta over t, because that's basically the same thing, and we knew that omega was theta over t. So we can just replace theta over t with the omega, and then we already found omega, so we can just put that in. So it's just about manipulating the equations that we already know to make it a little bit more efficient to solve the problem. And so again, we got 168 pi over 5 centimeters per second. A satellite traveling in a circular orbit 1,800 kilometers above the surface of Earth takes 4 hours to make an orbit. The radius of Earth is 6,400 kilometers. Find the linear speed of the satellite. All right, so here we have the Earth, and we've labeled the radius of the Earth, and then how far above the Earth the satellite is from the Earth. And here's our satellite, and it's orbiting the Earth, so there's the path that it's taking. And then we're going to find the distance the satellite travels in 7.5 hours. So first, let's look at the linear speed of the satellite. We know that the radius of the orbit is the total of the radius, it's the sum of the radius of the Earth plus how high above the surface of the Earth that the satellite is. So our total radius is 8,200 kilometers. And so we know our arc length is 8,200 times 2 pi, because it's going all the way around the Earth. And then we know that our linear speed is just that arc length over the time. So we can plug in that arc length, and we knew it takes 4 hours, so we put the 4 in for time. And then we simplify, so we get 4,100 pi, which is approximately 12,881 kilometers per hour, which is pretty fast. So that's the linear speed of the satellite. Now we're going to find the distance the satellite travels in 7.5 hours. So remember that distance is the same as velocity times time, because if you look at this formula we just used for linear speed, if you multiply both sides by t, then you get vt equals s, which is the same thing as s equals vt. So then we can just plug in our velocity, which we just found, and it's better to use the exact answer and then approximate later. So then you multiply that by your number of hours, and you get approximately 96,604 kilometers. So that's how far the satellite's going to travel in 7.5 hours, which makes sense because in 1 hour it was 12,881, and that was kilometers.